Here we need to make the definition of a manifold. Generally, a definition of manifold, we say that a manifold is any set of points such that for each point there is neighborhood, or by other word, it's open set, and we call it also neighborhood in green. For example, for instance, in a way that each point could be mapped to another point in open subset in Rn. Of course, the manifold we are talking in the order n, so the same order, the both. So a manifold is a space, Rn is a space. For any point of the manifold, there is open set or open subset, such that could be mapped onto a point of open subset of Rn. And the word onto is not arbitrary. I mean, it has a meaning. That means for every point in Rn, there is inverse image. And we are talking now about map. And map is another word to say function. And map should be one-to-one. So it is not function here. It's a kind of function that one-to-one. And this is all what we need. A map on one-to-one. From open subset to open subset. The first is the manifold. The other is Rn. Such that for each point in this open subset in manifold, there is image according to this one-to-one map. Is there any other requirement for this map? No, just that one-to-one map. So, for example, we don't need to preserve the length or angle or anything. And this open subset shouldn't require or shouldn't cover all the manifold, or doesn't require to cover all the manifold. Actually, the general definition of the manifold, we just need to take an open subset of this manifold such that there is a map. For other point who is of course, who has another neighborhood, there is another one-to-one map. So and we call the couple of any subset open subset, and this map, this one-to-one map, we call it chart. So this is just definition, just name. We call it name. And the union of charts that cover all the manifold, we call it atlas. When we say what is open subset, also open, I put it in practice between brackets. Why? Because when we say open, that means for each point there is neighborhood. For example, if I take a circle, I shouldn't take into consideration the circumference. If I take the circumference into consideration, this is not open subset. It will not be open subset because the point on the circumference doesn't have a neighborhood. In such that, for example, I suppose that you are familiar with the definition of neighborhood in mathematics. You can say for each other point, such that there is point between them, such that we can use epsilon bigger than 0, so that we can define it. I mean, you can find it easily in open subset, in the definition of open subset in any reference. So, to say it is manifold, it's enough to consider these these properties. And as a trivial example of manifold is a sphere. A sphere you can, as illustrated here, a sphere is 2D. For example, we take just the surface of the sphere. We don't take the volume. This is 2D. So n equal 2. So there is map, for example, for each point there is map into R2. And R2, there is kind of, for example, if we take 2 points to cover the sphere, we need at least we need two shards to cover all the sphere, because it is by definition is a just consequence of the definition. When we say open subset, you shouldn't take into consideration the circumference. So at least you need two open subset that there is intersection between them. The intersection is illustrated in green. The first open subset is U, the other open subset is V, and every open subset there is a kind of map, one-to-one map. The first V1, the second V2. So there is a kind of other definition, we call it the overlap of shard. Overlap of shard is such that if we consider just the intersection between them and we define it by phi2 composition phi1 minus 1, and this is clearly the domain of this function, of this composition of the two function, is Rn, and its arrival also Rn. And here why you can ask this you have the right to ask why I can take phi 1 minus 1, because by definition I said onto, I said it is one-to-one map, and so this function has inverse. So I can not necessarily unique, but at least has an inverse. So this is what I want to say. And here the arrival of phi1, the arrival of phi2 is R2, and it's clearly just coordinate system. I mean, for each point there is two coordinate here because R2, but in general n coordinate n indexes or n number that can be defined this point, the position of this point FB in Rn. So this is the general definition of manifold. So what is differential manifold? Before talking about differentiability, we need to have a look about continuity. How can we define continuous? In R, in Euclidean spaces, it's we can use usually Cauchy way, and we choose psi bigger than 0. But in manifold, we need to take more general definition. So let's talk about just two topological spaces. Of course, manifold is topological spaces finally. And the first is M, the second is N. And we talk, there is one-to-one map. We call it F here. We take open subset of M, we call it U, and a point of it, such that this open subset, the image of this open subset, also another open subset with Fu equal to V. Equal to V. We say F is continuous at a point X if there is open subset in M, U in this case, contain X, and open subset in the arrival topological space N. This open subset contains the image of X according to F, such that the image of U is containing in V. So I need to take two open subset. At least take it as small as you can. At least I need just one open subset, such that if you contain in V, if this condition is satisfied, I call it F is continuous, and F is continuous at X, and to be F continuous over this topological space M, it should be continuous for all x's, for all point in M. Once you define that the continuous term, it's natural and easy to define the differentiability. Now we can define the differentiability of F. The partial derivative of F should exist and continuous. The first and the second and until K, and in that case we call it differentiable of order K, or other word say K. And here we need to define another term which is also important, which called CK related. Previously I just have a definition quickly about what so-called overlap of chart. Also I need to have a look again about it, because it is crucial to define CK related here. CK related, what I call by CK related, two function to be CK related. For example, here F and G, and I take topological space, I take manifold for example, and inside it I take two open subset. There is intersection between them, U and V. The first, there is a chart associated with it. The second, there is a chart associated with it. That means there is one-to-one map that associate each point of U with a point in an open subset in Rn. I call it the first for U F, and for V I call it G. So now I have these two charts, and I take a point between in the superposition and the intersection, sorry, I call it for example here P. Since I can take the inverse, I can define G composition F minus 1, and this function, as I said previously, it is the arrival and domain Rn to Rn. So by other words, it's just coordinate transformation. I just use another map to find other chart to find the coordinate. So here, if the partial to be CK related, this FG, this is the couple of two function of two one-to-one map, to be CK related, the partial derivative of order K of this composition should be exist and continuous. If that's true, then it is CK related. And as I told previously about definition of atlas, is union of all charts that cover all the point of the manifold. And if I can find this atlas such that any two one-to-one map, such that any of these two of this one-to-one map is differentiable, so I can call it CK related manifold. CK related if any of these two one-to-one maps are what? Are CK related. That means the partial derivative exists and continuous. The partial derivative with respect to what? To x1, x2, x3, to the coordinate system. So this is the definition of CK related. Once I found the definition of CK related, I can just say the manifold is CK related manifold. And in more specific way, or in particular way, when k equal 1, I call it differentiable manifold. So differentiable manifold is very specific case or particular case of this definition, CK related manifold, which that's why overlap chart is important to introduce before we talk about differentiable manifold. So differentiable manifold, or more generally CK related manifold, is important in differential geometry because these properties of differentiability let me or give me the freedom to define many important concepts, including, for instance, tensor. As we see that the partial derivative are crucial to define tensor. So this is very important, and we can continue to other definition. Or before that, we will take some example of some trivial manifold. Namely, we will take about sphere or surface of the sphere as more generally, or in more detail, as an example of manifold.